Log on, tune in, find out. Another good idea from Cambridge.
A few words of welcome from me. Now, unless I'm in the wrong place, the first thing I've got to make clear is that this is the Algebraic Lie theory workshop, right? Because we are running two this week, really quite stretched, and the other one on discrete integral systems is being held over in the master class. In fact, we're really, as you can see, really just about overflowing with numbers. And that's, of course, because of the great program here. And I wanted to take this chance to say a really sincere thanks to the organisers, both of the program and of this workshop, because without their efforts, we wouldn't have the program and you wouldn't be here. So really, really grateful to them. Obviously, we are extremely busy this week with everyone here, but the staff, the only role of the staff is to help you and to make this as enjoyable and as stimulating an experience in a week for you as we possibly can. So if there is anything, any way that they can help or any query that you have, please don't hesitate to go to the desk and just ask. They're more than willing to help, and that's what they're here for. So I think it's probably, you don't want to hear me speaking. I think you want to get on with the workshop. So I hope you have a great week here. And over to Sasha now to chair this session. Welcome, everybody. Thank you.
Okay, so let me also make a couple of announcements. First of all, note the schedule change. Instead of Grainovsky's talk, we will have the talk by Alexei Sebastianov. I think this is the only change we have. Second announcement is that those who don't live at Wilson Court can still have lunch there. You just have to get lunch ticket. Or you can go to the city for lunch. But you can also eat here with those who live here. Next announcement is that if you did not indicate your vegetarian preference for the dinner, or you stopped being vegetarian in the meantime, you can still change your choice. It has to be done more or less after this talk or before the coffee time. And finally, some US participants should have gotten some form which you need to send to Oregon in order to get reimbursed. And if you didn't get one, or if you want to get one, ask the staff or talk to me during this week. Okay, so now the first speaker today is Iain Gordon from Edinburgh. He will speak about crystal structure for representations of Cherednik algebras.
So thank you for the invitation. I should begin with an apology. I know that these lectures are videoed. I have even been watching some of the videos, and I've seen videos from the introductory workshop. I've been trying to keep track of where my PhD students have been sitting. And as I was watching, they were getting further and further back in the rows. And I started to give them a row for this, for not being engaged. But I have to apologize to the people in the front row. I have a terrible cold at the moment. So I hope that you don't catch this. And my PhD student, as you would see, if he puts his hand up, he's sitting in the back row because he's been warned. Okay, so I want to talk today about rational Cherednik algebras and particularly some work of Peng Shan. It's on the archive now. Number this. And this is also work that's very closely related to work that I've been doing with Maurizio Martino. And what I would like to do is explain what Peng Shan has done, put it into context, but I'm going to explain what she's done, but using the proofs that Martino and I have, rather than the approach that she has, although it's very closely similar. So everything that will be in the second section is essentially due to her, although the proofs I present will be different. And I want to put it into some context and relate what's happening to Hecke algebras as well. Okay. So throughout the talk, we'll fix some positive integer, and then we'll have another integer. This one will be fixed, and as we go along, this one will be varying here. And we'll have the group W, which depends on R and N. This is just going to be the Reith product of a cyclic group of order R. So the rth roots of unity, Reith product with the symmetric group. So we take N copies of these and then let the symmetric group act by permuting them around. And then this acts on n-dimensional space, just because you have one copy of the roots of unity acting on each space, and then you have the symmetric group moving things around again. And this is an action by complex reflections in general. So if R were equal to 1, of course, it's the symmetric group. If R is 2, it's the Weyl group of type B. And then in general, it becomes a complex reflection group rather than a Weyl group. If I want to look at the reflecting hyperplanes, I'll call that set A. So the place where the group acts freely is when I remove these, like so. And then inside here, I just need to have a name for if I have a reflecting hyperplane. It's going to be defined by the vanishing of some functional, which I'll call alpha L. And then the elements of the group that fix this hyperplane form a cyclic group. Let's call it WL. And then I can look at inside the group algebra for WL. I can look at different idempotents corresponding to the different one-dimensional representations, which I could just realize as powers of determinants. For instance, if I were to pick if I'm thinking of the action on Hn, so these are idempotents. I going from 0 to however many there will be for this. And the set A is actually going to decompose essentially into two different types of reflecting hyperplanes. Ones where the sort of thing fixing a hyperplane is conjugate to an element from the symmetric group. So sitting inside here, there were the symmetric groups, so I could just look at the ordinary planes, the ordinary hyperplanes, or their generalizations. So that then the fixed points, this would be size 2. That will just be like that. And this one are conjugate to elements from the roots of unity instead. If I was just to take, say, an element from mu r, a non-zero root of unity, put that in the first place, and then just take 1, 1, 1, 1, 1, 1, 1. That produces an element inside here, which is also acting by complex reflection. And the things that are conjugate to that will form a second class, like so. And so this is essentially one conjugacy class. There's a number of conjugacy classes here. Okay. So now, we want to define the rational Cherednik algebra, which is going to be associated to this data. So this depends on some parameters. Now, in general, the parameters, when you start to choose this, the parameters can be arbitrary complex numbers, but I'm going to restrict what's happening, which will be important in certain circumstances, just to the rationals at the moment. Although we expect, I think, that actually dealing with the rationals, if you could understand all the Cherednik algebras where you deal with the rationals, then you would more or less understand everything up to Morita equivalence. And there should be a condition here that says the sums of the capital K's are equal to 0. Then this algebra sits inside the polynomial differential operators, which I've got potentially poles along the reflecting hyperplanes. Smash this group here. So we also remember how the group acts on here. And it's generated by 3 parts. So it's generated by the regular functions on Hn, so that's a polynomial ring in n variables. We have the group elements as well. And then the last one, these are the interesting operators. These are the Dunkel operators. For any vector inside Hn, we look at the directional derivative in that direction, and then this. Okay, so these are Dunkel operators. So these operators depend on the parameters. Here's the k, here are the capital K's. The deformation, so this is, if you were to set all of these equal to 0, you would just end up getting differential operators instead. When you put in these parameters, then you start to pick up poles along reflecting hyperplanes, but just poles of order, simple poles here. And these things are taking values inside the group algebra as well. These are elements which came from the group algebra. And the remarkable fact, the classical fact now, is that these Dunkel operators commute with one another, okay? Which a priori isn't at all clear. So this is the Cherednik algebra is the algebra sitting inside here, defined by these 3 sets of elements, generated by these 3 sets of elements. And it's a theorem of Ettinghoff and Ginzburg, who first introduced these algebras, that, remember we said when all the parameters are set equal to 0, this then just produces this ring here. And it's a theorem of Ettinghoff and Ginzburg that says no matter which values of k you put in, as a vector space, or there is a natural PBW basis for the Cherednik algebra coming from things from this, and things from this here, that will produce a basis for all of this, just as you had a basis here. And so it's somehow, these are flat deformations of this. That's the point. Okay, so we have now a family of deformations of W equivariant D modules, if you like. And it's an obvious question at this point. The way that this is sort of presented, the PBW theorem of Ettinghoff and Ginzburg tells you, in particular, these algebras here have a triangular decomposition. The part that comes from here, the part that comes from here, and the part that is to do with the polynomial ring in these variables. And so you can start to do classical things from Lie theory, and in particular, you could define category O. So category O here will just turn out to be finitely generated modules such that the differential operators act, or these deformed ones, these Dunkel operators, act locally nilpotently. Normally for category O in the Lie theory case, you also have to put some condition on how the Cartan acts. But here, the analog of the Cartan is the group algebra over the complex numbers for a finite group, and so everything is forced to be semi-simple for you anyway. You don't have anything extra to do there. Okay? And then, having made that definition, you can construct Verma modules. So these Fermat modules replacing weights, you take irreducible representations of the group W here. Now, these are understood combinatorially as just being R multi-partitions of n. So for instance, when R was 1, you just get partitions of n. That's the symmetric group. When R is 2, it's file group of type B. You get pairs of partitions, and so on. These label the irreducible representations. And then your Fermat module is just defined by induction, where you kill the action to do with the Dunkel operators and the group. So here we put in the representation of the group, so W acts just as it should, and these operators all act as 0 on here. This is a well-defined representation. This is the Fermat module, and it has a unique simple quotient, which is the simple module, L. And these give you the complete list of simple modules inside this category here. So in particular, there are only finitely many simple modules. So if you want to push the analogy further, this category O you should really think of as something like an analog of category O for simple complex Lie algebras, but where you've also chosen a central character at that point. That's sort of analogous to the choice of your parameter k here. So there are a finite number of objects, and the basic question is, of course, this. What are the multiplicities of the simples in the standards? The standards are easy to understand, say, in some sense because of the PBW theorem. It's not difficult to write out a good basis for them and understand things like characters. And so the question is, how could you try to describe the simple modules? Okay, and there's a conjectured answer to this by Xavier Yvonne. Which goes as follows. You start with a R tuple of integers here, and another positive number. And then to these things, you're going to associate certain choices of parameters. So Yvonne's conjecture is only made explicit for these choices of parameters. So the first one, the k, is 1 over e. So that's the k is the thing in the deformation that appeared attached to something to do with the symmetric group. And then there is an awkward definition for the ki's. These were motivated really by results to do with Hecke algebras associated to these groups. So Yvonne suggests that you take this for your ki's, and for the rest of the talk, we'll stick with that. And I should say, this doesn't quite satisfy the condition I wrote. That will then force you, because we take the sum of the k's to be equal to 0, that will enforce a relation for k0. Okay. Then, so attached to this data, we have a representation fs, which is the level R Fock space. With multi-charge S. So I don't want to explain precisely what this is, but rather give you some of its important properties for the rest of the talk here. So the properties that this has, first of all, this is a representation of a quantum group. So we take affine SLE hat, and this thing that we're going to take here, this is the central extension of the loop Lie algebra. We don't have anything to do with the grading or the derivation in here. So it's a representation for this. This one here, it's of level R. Yeah. It's very far from irreducible. So often when you look at Fock spaces, you may also have an action of a Heisenberg Lie algebra acting. There is a Heisenberg acting here, and it's still not irreducible when you put both of these things in as well. It has a basis, a standard basis labeled by elements, multi-partitions again, where we let n vary, so R multi-partitions produce a basis. And then it has a canonical basis. In fact, I should really say upper. It has two canonical bases, an upper one and a lower one. This was constructed by Prof. And you can also produce a crystal. So it has a crystal basis, which goes back to work of, I think, Jimbo, Mishra, Miwa, and Okada. Okay. And then Yvonne's conjecture. Predicts what these composition numbers should be here. Well, they're supposed to be the transition matrix to get from the standard basis to the canonical basis. So where d lambda q is the transition matrix in standard. Pardon?
It's for a totally different algebra, probably.
Yes. Yes. So I'm going to try to put the point about the work of Peng Shan that I want to explain is that this starts to put this into some context, this conjecture. I don't know, maybe other people do, but I don't really know any good reason why this conjecture is true, whether it's true or not. But I want to put it into context to explain a little bit about why we might start to believe this and how this fits in with some other known results already. And there are ways that people are starting to look at this. There's work of Varignolo and Vassero, which tries to relate what's going on in category O here to certain types of affine parabolic category O's. These polynomials here are, of course, certain types of affine parabolic Kashtan-Lustig polynomials. And so there's geometry in the topology in the background associated to this. Okay, so I want to make some remarks about this.
So does this conjecture potentially tell us, for example, which of the L's are finite dimensional? questions like this. What other supports and so on?
Aha.
Or is
Well-
it too complicated to tell, even if you know how to prove it?
I think it's too complicated to tell, even once you get down to, you get some Kashtan-Lustig polynomials, and then you have to hunt for certain coefficients being non-zero or zero.
Yeah.
And I think that's too complicated at that point. But I do have something to say about that at the end, which is exactly opposite to the question you just asked, which would be which things survive under KZ. For sure. Okay. Okay, so this object here is constructed from a set of integers s, but it has some sort of periodic structure with respect to E. And if you choose another S, which is congruent modulo E, then you get the crystals being isomorphic. But they're not the same. So the crystals are coming with a certain labeling to do with multi-partitions, and when you start to vary this S, you get exactly the same crystal, but the actual basis elements that are being chosen in the crystal or being labeled by it are going to vary as you vary this S around. There's a very concrete combinatorial description of how to get the crystal basis. It depends on some ordering on multi-partitions, and that ordering depends not only on S modulo E, but on S itself. Okay? If you look at the part that starts off at the trivial multi-partition, so that's at the n equals 0 thing, remember this representation wasn't irreducible. This produces one irreducible component, which is the same as the representation gotten like this, where these are the fundamental weights, and I count these numbers modulo E. Okay, so this is a representation here, and this object is known that it controls the representation theory of Hecke algebras. I'll just define these Hecke algebras in a minute. This is due to, this was the conjecture essentially of Lescure, Leclerc, Thibon, which is then proved by Eureki, and understanding the crystal as well. It's nice in work of Gronowski. Okay, so what are these algebras? So the HQ, these Hecke algebras, these are the Eureki-Koike algebras. So I have generators T naught up to Tn minus 1. It's an algebra over the complex numbers. And these are supposed to satisfy the braid relations associated to this. So there's 0, 1, 2, up to n minus 1. So they satisfy those braid relations. So it looks sort of like type B, except we also then put in a Hecke relation for the TIs where I is positive. So that's one Hecke relation, that's when I is positive. And then at the 0 place, this is supposed to play the role of the relation for the cyclic group of order R, and it looks like this. So these numbers, these S's that are being used to define the Fock space, they're appearing in the definition of this Hecke algebra. And so what you're seeing is that the Hecke algebra is somehow specialized to an e root of unity, because you're factoring out by e here. And then you have these integers s. And in particular, in this Hecke algebra, it only recognizes what's going on with s up to modulo e, okay, inside this. And this has, in particular, part of the consequence is when you look, well, let me say something else here. I should say this is a Riki Koiki.
So for r equals to 1, this coincides with the Rouquier theorem, this conjecture.
Exactly. Yeah, I'm about to say. Yeah. Well, yeah, I should say something extra. Okay, so the canonical basis. So the thing that's appearing in Yvonne's conjecture depends crucially on S, not even modulo E. So even if you look modulo E, Yvonne's work showed if you look at the canonical basis for one value of S, take another value where it's conjugate modulo E, the decomposition matrix has got different numbers of non-zero entries. So there's something even more serious happening. But it's always true, thanks to the theorem of Ariki, that if you just look at this part associated to this trivial multipartition, so this part here, the canonical basis doesn't really depend on your choice of S modulo E, it's just moved around by permutations. Okay. Then when you take your parameters S to be very far apart from each other, then it's a theorem of Rouquier that category O is equivalent to the so-called cyclotomic Q-Sure algebra.
You mean to category of representations?
Of which? Of this one? This is a finite dimensional algebra, so I mean all of its representations for this one.
This is, what is it supposed to be n or?
Oh, that's in type A, so I don't want to say the full definition in general. Okay, but there is a Q-Sure algebra, or a cyclotomic Q-Sure algebra that can be built from a Hecke algebra by looking at certain types of modules and looking at their endomorphism ring. This was something that was studied long ago and introduced by Dipper, James, and Mathas, I think. And this equivalence is due to Rouquier. And in particular, when R is equal to 1, so you're just in the symmetric group case, decomposition numbers are known for these by work of Varignolo and Vassereau, and this agrees with the conjecture of Yvonne here, in that case. And also, the conjecture is true for large E, because for large E, once E gets big enough, somehow bigger than something to do with the number n, then there's recent work of Brundon and Kleshchev that will allow you to say, first of all, that these Hecke algebras that appear are isomorphic to degenerate Hecke algebras, which then have nice coverings by parabolic category O's, and using the theorem, the work of Rouquier on quasi-hereditary covers, you can see that it's okay as well, the conjecture. But that's not really the point. This is somehow large-scale behavior, and what's interesting is not large E here. Okay.
Is it known for n equals 2, this conjecture?
I don't think so. No. I don't even think it's known in this regime here. Yeah.
But wait, in your previous example, this conjecture follows from this.
So in this equivalence here, if we were then also, so this specifies a certain choice of parameters. If we were then also to assume that R was equal to 1, then this is genuinely a Q-Schur algebra whose decomposition numbers are known, and it agrees with what's up here. These are known to be certain types of parabolic Kashtan-Lustig polynomials, and it agrees. This is
Maybe I didn't state clearly. I wanted to ask if rank 2 is known.
oh, rank 2.
Yes.
So like a
Yeah.
oh yes, I think it should be. It's maybe not written down, but it's easy enough to work out the combinatorics to check that. I think so. You mean rank 2? So I'm allowed any cyclic group,
Yeah.
but n is 2.
Yeah.
It's certainly okay for B2, right, which
Yeah,
is
yeah.
Chumatova's work, and then people have got enough combinatorics around now of diagonalizing modules and so on, using this Dunkel Cherednik, this commutative subalgebra inside the Cherednik algebra to be able to say enough, I think, to make sure that it's true as well. But that hasn't. I mean, the combinatorics when you actually have to write it down is ugly if you don't do it right. So I don't think anybody's written that down. Yeah. I should also mention here there's another way to understand in type A. So when R is equal to 1, the decomposition numbers here, which is due to Suzuki. Okay. So let's take the sum of the Grothendieck groups of category O's, complexify it. So that's now a vector space which has got a basis given by the multi-partitions. Then this Fk is a module for this loop algebra, which is just that Fock space representation above when Q is equal to 1. And if you look at the basis given by irreducible representations, as you run through all n, together with some type of induction and restriction, which I will define. This is a crystal, isomorphic to the crystal. That plays a role in Yvonne's conjecture. So this ties, in a combinatorial sense, the two sides together. And the thing I want to do is I just want to explain a little bit about the proof, because the construction of how to get these nice induction and restriction functors is quite pretty and rather more general than just the situation that we're in here. So one starts with an arbitrary point inside.
A crystal, you mean a crystal with respect to what? With the operators of,
Yeah,
crystal
so
operators of SL.
yes, SLE hat are going to correspond to some kind of induction and restriction functors. They will provide a crystal structure on this set that agrees with the crystal structure from this work here. So
what will be the vertices?
the vertices will be labeled by these multi-partitions, but they will be corresponding to the simple representations inside category O.
Oh, I see. So the original basis in SL of SLQ will be modules, and the induction restriction will be the E's and F's.
Yes. So the natural, the standard basis that comes for free corresponds to the Verma modules. And then this basis here, the simple modules, will be the crystal basis. So then Bezrukavnikov and Ettinghoff. So this is the reflection representation of our group. Bezrukavnikov and Ettinghoff defined some induction and restriction functors, which will go from category O here. You restrict or you induct, and it goes to a different category O, one related to the stabilizer of your point X, so that's some other complex reflection group. There are Cherednik algebras associated to each of these, and so they define induction and restriction functors, and these are exact, and with a bit of work, they are adjoint to one another.
Adjoint on both sides in this case.
With a bit of work, yeah.
Can you prove it for any Coxeter group? For any group that they are adjoint on both sides?
I don't want to say, I can't remember how much we use about this specific situation. Not for anyone, because we use things to do with Hecke algebras being well behaved. So I would have to remove some of the bad complex reflection groups where it's not known that Hecke algebras are well behaved to start with. And then there may be some other ones I don't know.
But real reflection groups, you think it will?
I would have to have a look to see exactly what we've written down, to see the generality of that. So if you choose the specific case of this point, where star is something non-zero, so that's basically some point there, non-zero. It has stabilizer one group smaller, and so therefore you can produce restriction and induction, which will go from Wn to Wn minus 1. These were exact, and so they induce some functors on the K groups, and they produce E and F acting on that space there. But we need to get EIs and FIs if we want to get the crystal structure here. And so there's another important ingredient in the work of Bezrukavnikov and Ettinghoff, which is the following. We haven't said exactly which value of x we want to pick. And as we choose different values of x's, then the functors are always isomorphic, but they're not really canonically isomorphic. And what's happening is these functors have got monodromy with respect to this x as well. Okay? So as I choose different x's with exactly the same stabilizer, I get isomorphic functors, but then as I have a look to see what happens as I move around loops and so on, then something more interesting will happen. And what you get in this situation here, instead, you get restriction functor from n to n minus 1, where I'm allowing here this x to vary. It goes to here, plus a local system on C star. And this local system even has some residue of the equivariance of modules with respect to Wn here. It still has an action of the normalizer of this thing here. And if you have a look at this for one moment, you see that you could take the very last copy of the roots of unity acting on here. That will commute with the Wn minus 1 that's in here. And so that embeds into there. And so in particular, you have some equivariant monodromy with respect to this mu r, or a local system, if you take monodromy, then you get not only this, but also a representation of the fundamental group of C star. We can factor out UR, choose the base point that we chose before, like so. And so we get an extra matrix, if you like. This is just a cyclic group, a cyclic group of rank 1 here. And if you have a look at the representations that occur from category O, and representations occurring have eigenvalues, all powers of x 2 pi minus 1 over e. So therefore, in addition to just looking at restriction, we could project onto generalized eigenspaces here too. So project to generalized eigenspaces. And that then produces, we have a choice for each generalized eigenspace between 0 and e minus 1. That produces functors ei and fi, which then act on here. So this is the construction of how to produce the EIs and the FIs. Peng Shan has a different construction of how to produce these. The way that you do it here is slightly more flexible because you don't have to just look at Cherednik algebras associated to the situation we started with. This works in a little bit more generality, so it can be slightly more geometric, perhaps contains interesting information. So now part A, we've got these operators now. Part A follows by calculation on what happens to the standard modules. They provide a basis for this space up here, and you can calculate explicitly what happens, and you see that you get this nice representation. And then part B is just an application of two more general theories. So the EI and the FI make what's called an SL2 categorification. So that's a theory due to Chung. And Ruquier. So for that, you have to look at endomorphisms of your functor. So you have to look at things commuting with the action of the functor EI, and that's the action of the generator here.
So what does this fancy term mean? It means they actually act as SL2 module? Or?
This?
Yeah, SL2.
Well, it means, first of all, that they act as an SL2 module. Then you also have that the simple modules inside the category should belong in weight spaces. That's fine. That's just this weak SL2 categorification. And then there's the crucial aspect of it for what's about to follow, is you have to have some way that the functors are behaving in a very rigid style. And so you look for extra structure, that there's something commuting with restriction here. That's this operator X. There's going to be another thing called an operator T. And these two things together are supposed to satisfy some coherence relation that look like the relation for a degenerate Hecke algebra. And when one has these two things together, one has much better control over induction and restriction. I mean, you have extra operators that you can try to let act and so on. You have much better control, and you get for free, or through the work of Chung and Ruquier, many extremely nice results, including one that I need to mention here. So the SL2 categorification is this being an SL2 module plus this extra data that I'm just saying here.
So when you say these things act, they act linearly.
the second operator acts on the restriction squared. The restriction squared, if you just think about doing E at the moment, that would be restricting from n to n minus 2. So that would be putting in 2 values in here instead. And then when you have 2 values, you have the braid group associated to having 2 things in here, and that produces the braid group of rank 2 here, which in particular has something corresponding to a reflection. And that's exactly what produces this T here. I'll just write that like so. Okay. So the thing corresponding to a braid crossing produces the T. And the crucial result that comes then from Chung and Ruquier is a multiplicity 1 result, which says that if I could well-define an operator that says I start with a simple module, and I could induce. I induce it, I get some new complicated object, but it has a simple head. That's a consequence of their theory, that multiplicity 1 result, and similarly for the restrictions. Okay, that gives you operators related to the induction and restriction that are supposed to be the crystal operators. And then there's some theory of Bernstein and Kazhdan on things called perfect bases. That allows you to then say that with these operators and these representations, we do produce the crystal that we first thought of.
I'm sorry, I didn't understand. So, in the case of generic parameters, these functors are the same as for the group W, yes? So, in particular, if you act on a simple module, you get a semi-simple module. So, how come then there is a...
Oh, but I've got this E here. I'm not allowing myself to be in that situation.
Ah. So this result, it's some kind of delicate result that tells that this module has a simple...
So if I was in that situation, which I think would apply, what will be happening? If I induce, I do get something semi-simple, but this extra fact of how the monodromy acts, this part here, will then allow me to separate each of them out, which is essentially by content of box or something like that. That's exactly what happens in that situation. Okay, so
Your crystal operators are the EI hats, the little EI hats.
yeah, and the FIs.
But is there any crystal limit in all this? I mean, you start off with an SL2
This is-
module.
This is just combinatorics here. We're not doing anything. There is nothing to do with the Q appearing at this point to try to take a limit or anything like this. I think.
Normally, crystals, you've lost the linear structure. So
Yeah, so this was just picking a particular set of elements inside here, these ones, and then showing that these EI twiddles and the FI twiddles then act exactly as you would on a crystal. There is the action of the capital EI and the capital FI on the whole of the Grothendieck group that will be producing an action of SLE hat, a real ordinary representation. But we don't have any version yet where the Q appears, which you would expect has something to do with the grading, so on. We don't have any control over that. In the original, I mean, historically as well, I suppose it went that direction, that the work of Jimbo et al., who found the crystal structure on this fog space that was then upgraded to the canonical basis work of Huckel.
But somehow the principle is that you should lose some of the relations, and some of the lines in the graph should disappear in the crystal limit.
That's exactly what's happening here. We're losing a lot of information by only looking at the head. That's killing an enormous amount of information, and lines are being lost from what you would expect. Yeah. So I want to tie this up now. To the following part. We have this crystal structure, but remember the crystal structure really, we've got a fixed S here, but this theorem only tells you that you get something which is isomorphic to that crystal, and we don't have good control, for instance, over what is the real description of, when we look at the crystal, what it will be producing is, for instance, let me say this like this. We look at this space here. It's this Fock space. So you've got the crystal. We know it decomposes into infinitely many different irreducible components, which combinatorially can be understood from the work of Jimbo et al. We have a similar thing here, but what will be being produced is just a bijection between combinatorics rather than an equality. And we need to understand, if we want to get closer to Yvonne's conjecture, where the choice of the specific S is highly crucial because decomposition matrices genuinely vary rather than just being permutations of each other. We have to see that this labeling really has something to do with the natural labeling of the crystal for the corresponding values of S. Okay, so hidden in the background to all of this, there's something called the KZ functor, which goes from category O to representations of the Hecke algebra, like so. This is analogous, if you were just doing the case R equals 1, where you were looking at symmetric groups, this is analogous to the Schur functor. This can be, in the context of what we've just been talking about here, this looks like restricting from all of n to a generic point inside the reflection representation, one that has no stabilizer at all, and then taking monodromy. This produces the KZ functor here. So if we look at the multi-partitions here, as we run through all of n, where the KZ functor doesn't kill a simple module, let's call that set 1. This thing here, by properties of this KZ, will parameterize the irreducible modules for this Hecke algebra. This is not semi-simple in general. It parameterizes the irreducibles for this, and this is equal to multi-partitions appearing in the crystal of the Fock space genuinely associated to the point S. So we look at that component that includes the trivial multi-partition. There is a crystal structure on that, and as we vary these S's modulo E, that crystal stays the same, but the way that you label the irreducibles or the multi-partitions in it varies. And what we're saying is when you take that specific S that defined K here, you get an equality. It's not a bijection here. And so that has, these types of partitions are sometimes called Ugloff partitions, and they're generalizing partitions called Kleshchev or Ugloff multi-partitions. Generalizing, in the symmetric group case, Kleshchev partitions. So a corollary is the crystal theorem is, let's call it natural. So the parameterizations really do match up on the nose, or they seem to be matching up on the nose, rather than just up to bijection.
So is the point that there are these modules with full support of Cherednik algebras, and there are representations of the Hecke algebra, and in type A, there is more or less only one bijection that you get, up
Yes.
to flip.
Up to flip by the side.
Yeah, by the side. But in this case, you get many bijections.
Exactly.
Once you go into type B, you already have many bijections, which are parameterized by residues modulo E of a collection of integers.
They're parameterized by more than that. It's even more than that.
Oh.
Yeah, so that's the thing. That parameterization is part of it, but there's more than that going on. Exactly, I mean, what's happening when you look at the residues modulo E, then you can still have lots of different parameterizations for each one. And this is explicitly telling you what the things,
What you get.
what you get. Yeah. And so the proof of this uses work of Jacquin, who introduced something called an A function, which goes from multi-partitions to the rational numbers. And he showed that one can label the irreducible representations of this that there would exist a unique, given an irreducible one, exists a unique multi-partition such that the decomposition number associated to, say, a Specht module of that is non-zero, and it's minimal for the minimal such for AK. What I want to say is, if I say this in words, there's a canonical way, given a function which is related in the real cognitive group case to the A function of Lustig from Kashtan-Lustig theory, there's a canonical way to produce representatives of irreducibles inside the Hecke algebra. And for some time, I think it's not really properly understood where these irreducibles are coming from. But it's certainly true that Jacquin, using Arrighi's theorem, identified the set that gets produced this way with the Ubloff multi-partitions. And on the other hand, there's a work of Dunkel and Griffiths, who answers some question of mine that has as a consequence AK respects ordering on category O, which was a highest weight category. This function produces to every simple object, it produces some number, and you only get decomposition numbers when the numbers are appropriately comparable. And from this, you can check with a little work that the set 1 is the set that appears in Jacquin's work, which is sometimes called the canonical basic set. Which then allows us to make this identification. So this has hidden in it some hard work here, and also it has hidden in it, this function really comes from studying things to do with Hilbert schemes and other resolutions of singularities inside it. But you can actually get on the nose exactly which things are killed. And I would suggest a conjecture. Canonical basic sets exist for all finite cognitive groups and for large families of complex reflection groups. I would conjecture that the set here, the lambda, where kz is not equal to 0, equals always the canonical basic set, which has played an important role recently in representation theory of Hecke algebras, and would give meaning exactly to what these labelings of irreducibles of Hecke algebras really mean. They come from the Cherednik algebra, and this fits with series of conjectures by Bonafé and Jacquin around this area and actually comes very close to proving many of them. Okay, thank you.
Question or comments, please?
Does the AK give a truncated multiplication, which is associative?
It's not known because for these complex reflection groups, when you move away from the constant group case, Kashtan-Lustig bases are not known to exist. If you do take, say, type B, though, you get this phenomenon where you can have Kashtan-Lustig theory for Heck algebra. The Heck algebras depend on 2 parameters. The Kashtan-Lustig theory that we're used to only has 1 parameter, really, 1 Q. Now there are 2 parameters going around, and there are conjectures about the existence of Kashtan-Lustig bases for these things. And in that case, this function A plays exactly the same role as it did originally in the work of Lustig in 1 parameter, and it would produce things like asymptotic algebras there. Part of the point of this is trying to understand what happens for complex reflection groups and hunting for exactly the types of things that you're asking.
You're looking for a truncated algebra, right? I presume, for some reason. I mean, would you believe that there's this truncated algebra?
People are looking for that. I don't know whether I believe it or not. I'm just saying that the combinatoric that has been defined, which was motivated exactly from the way that you're meaning, and had applications in Heck algebras that might point towards something like this, has a use here as well. I don't know whether these things exist or not. And they maybe don't, if they do exist, they maybe quite don't exist just as the generalizations immediately of what we had before.
The truncated algebra that Lustig uses has actually some information, gives some information on the representation field.
Yeah.
So are you expecting something like that too?
One would hope so. I mean, there's information here about the representation theory of these Heck algebras, which classically would be related to representation theory in other situations.
Of the Cherednik.
Well, this is the A function definitely has something to do with the representation theory of the Cherednik algebra here because of this result here. When you look at the category O, it's the highest weight category. It's the highest weight category for an ordering that can be defined by this A function. And so any time you have composition factors inside a standard, they have to respect this kind of ordering here. But this function is quite difficult to see from the world of the Cherednik algebras. It's not the most easy one to construct. So I think there's some content here.
Can you tell from this which reducible modules are killed by the symmetrizer?
I haven't thought about that yet.
So there expected to be a prediction from the theory of quantum homology.
Okay. I didn't know that. Yeah.
And
I
so
see,
it would
yeah.
be interesting to check if the prediction works.
Okay.
Because there is some grand system of conjectures that this would be a check for.
Okay. Yeah.
And we will resume at 11:30 by this clock.